Hello again, class, and we are back on chapter 4, part A, and this time we'll be looking at examples and problems. Yay! I'm sure you're quite excited. All right. So, the first slide that I've stopped on in my presentation is, hold on, slide 6. It's behind the image here. Okay, so on slide 6 I have two examples that I picked from the textbook to at least show you. We're not going to spend too much time on them, but example 4.1 and 4.2, both of these have to do with calculating the total charge. In one case it's a tube 10 centimeters tall, and it has a certain charge density, line charge density given. And the second example is a disk that also has a surface charge on it. The charge density is not given, but what is said is that the charge density increases linearly from R0 at the center to 6 centimeters per meter square at R equals 3 centimeters. So it goes from 0 to 3. So given that information, or it goes from 0 to 6 coulombs from R equals 0 to R equals 3. So given that information, we first have to derive rho s, the surface charge, and then once we have that, you then integrate it over the surface to give you the total charge. So basically both these examples use these formulas to derive total charge. Okay, so I'll leave you to walk through them because I think you'll learn more by just walking through them yourself than me having to walk you through every step. All right, moving on to the next slide, 7. Here there's a problem from the back of the chapter that I will look at. And so the problem is similar, except that we now have a cylindrical volume defined whose charge density is not a constant, but it's a function of both r and z. So it's given as 20 rz, and r is always less than or equal to 2 meters, and it's a cylindrical volume, right? You can imagine a cylindrical volume, and z, the height, goes from 0 to 3 meters. Okay, so given this information, let's see how to solve this. So here it is. So we have a cylinder, and it's centered at the origin, where the central axis passes through the origin, and to create the equation for Q, integrating it over the charge density. The charge density is given as 20 Rz. What is dV? dV for a cylinder like this is from our chapter 3 notes. It's R dr d phi dz, assuming all three exist. So R dr d phi dz, and here you have to put the appropriate limits, obviously. So R, the inside one, goes from 0 to 2. That's this, right? Then phi, which is this angle, goes from 0 to 2 pi because it goes all around really. And z or z is the height, it goes from 0 to 3 because given that it's 3 meters. So applying these three limits and doing the integration one step at a time, you can see the steps here, and it comes out to be 1.5 coulombs inside that cylinder. So the total charge on that cylinder based on the integration, and you can follow along the steps. I do the integration of the inside with just the r first, then once I have that, then I do it just with the phi next, and then there's a z that I probably forgot to write. Yeah, this is 20rz, right? So a z should appear here, but I'm sure you can, I'll fix it before I post this. Okay, so that z comes about, and then you do a d phi integration, and then you finally do a dz integration. Okay, all right. So that is a simple example or problem for -2. Let's move on and see where else we have problems. So we are now in the section called current density. I hope you remember these formulas for current density. And here, problem 4.8 on slide 9, it says that there is an electron beam. So this is a beam of electrons, right? And it's shaped like a circular cylinder of radius rho. So the radius is fixed, and it carries a charge density given by this. Okay, so rho v depends on a rho 0 is a positive constant, and the beam's axis is coincident with the z-axis. So I showed it like this because this is the z-axis, which is in the middle there. Okay, there's also a speed at which the electrons are moving in this direction, u, but we'll do that. That's part B of the problem. All we know is that rho 0 on the top is a positive constant. So determine the total charge contained in length L of the beam. So if this whole length is L, then find, which is actually we are deriving an expression. So this is more like a formula being derived. Then if the electrons are moving in the z direction with the plus z direction with uniform speed u, determine the magnitude and direction of the current crossing the z plane. Okay, so that is the problem. And I actually, this figure is not really for this problem, but I found this figure and it looks like this is a volume charge that is shaped like a cylinder, right? So I just brought this along so that it kind of helps you to visualize the problem. All right, so let's go to problem 4.8. I don't have a drawing here, so we'll just use that one drawing. So PV is given, coulombs per meter cube, using Q equals volume integral. So the volume integral has three limits, and the this dot dV can be written again as r dr d phi dz in cylindrical coordinates. So you integrate over the volume, right? And that integral gives you, it goes with these three integrals because it's a volume integral. So z goes from 0 to L, that is given, L is the length or the height. Phi goes all around, so that's 2 pi. And then r goes from some fixed, from 0 to r0. So all these are just in characters, we don't have any numbers yet to work with. So if you start applying those, you come up with this value for the integral. So here I have an integral r by 1 plus r square, which actually when you integrate it comes out this. So I substitute that into it, and finally this is the result for the total charge. Okay, so that was part A. Part B said find the actual current density, right? Well, actually it says find the current. So to find that, we have to first find the current density J, which is rho v times the velocity vector, right? So that is in the z direction because u is zu, right? If you want to assign a vector in this direction u, because u is shown like that, which is along the z axis, so that's zu, and then here ds, right, we need to do the I equals integral j ds. So I've given you the formula for ds also in cylindrical coordinates. So you have these three things. Now you put them together. Rho v, we know what it is, it's given. So if you integrate, first you do the scalar product of this and this, so the z's go away, so you're left with this surface integral, r goes from 0 to r0, phi is going all around, and there is no third integral because this is a surface integral, area integral. Um, and then if you integrate, you come up with I equals this. And the current direction is along minus z hat, right? Because current is always opposite of electron flow. So electron flow is flowing in positive direction, current is a minus of that. Okay? So this is the solution for problem 4.8. All right, let's keep moving. Example 4-3. So again, this is from your textbook. So let me skip to this, see if there's anything to tell you, or you can look it up yourself. Yeah, it's on page 184. It's very straightforward. We are using this formula on the previous slide with just 2 point charges, Q1 and Q2. So if two charges exist and they are located at these points in Cartesian coordinates, all you have to do is to find an electric field at a third point, 3, 1, minus 2. And also, if you place a charge of 8 into 10 to the power minus 5 coulombs at that point, what force does it experience? So you can see how he does it on page 184. Obviously, when you're given these Cartesian coordinates, you first have to create these vectors, r1, r2, r, and so on. So he shows you how to do that. The three vectors are clearly shown, and then he uses the formula, and he comes up first with E as a vector, the field intensity, and then the force, he multiplies E by the charge itself on the unit charge, or the located 8 into 10 to the power minus 5 located at that point, and so he gets a value for the force vector also. Okay, so pretty simple, I think, not much in the way of mathematical complexity or even understanding what he's done. It's quite straightforward. Okay, I'm going to move on to, let's see, slide 15, 16. Yeah, so here are two examples, example 4-4 and 4-5. But like I said before, it's not so much an example using some real numbers, but more how to derive a formula. So how do you derive a formula for E, the field intensity, if you have a ring of charge, right? And you can see on page 185 what a ring of charge looks like, and then how he goes about first creating that small element and then applying Coulomb's law to it to find the E from an element of the ring, and then he integrates across the entire ring to get the value of E. Same thing he does with the ring of charge, which is the next, sorry, that was the ring of charge. Then he does a disk of charge. A disk is like a dinner plate, right? So if you have a disk of charge with charge density rho s, which is here, right, rho s, then how do you go about deriving E? So I will let you to walk through them, these examples one by one. Please make sure you understand there is a lot to learn by looking at these two examples, because they give you a good insight into how you first set up that small element of, first you take that small piece of charge or element of charge, how do you apply Coulomb's law, and then you also then start to integrate by taking the differential approach and expanding it to the full surface or the full length. Okay. All right, with that I will move on to another example, 414 from the back of the textbook, from the back of the chapter. Now 414, actually I thought instead of trying to derive it in a more complex way by first finding the formula, or first deriving the formula and then applying the numbers, I was able to find a close derivation, not exactly but close. So this line of charge, the formula is when the line is AB and it's a certain point, it's on the z-axis. That is the problem also. Our problem 414 also is on the z-axis. Our line of charge is on the z-axis, but in our case the line begins at the origin, but here the line begins at point A and goes to point B. For us, it's been given that the line begins at z equals 0 and goes to z equals phi. But for the general case, this is the formula. So it still depends on all these factors, same factors. Rho L is the charge density along the length. In the denominator, we have 4 pi epsilon r, right? We know what all those are. And then the vector part, which has unit vectors, is along the r-axis and the z-axis, because these are as a cylinder, right? Most of everything we are doing here looks like a cylinder or a sphere, right? So that's what this formula comes out. If the line was infinite, then this is the formula, but this is not infinite, this is finite. So now if you take r as 0.1 meters, it's actually given as 10 centimeters, right? You can see we need to find the E at this point, 0, 10, 0. That means it's here on the x-axis, right? And 10 centimeters, 0.1 meter, so r equals 0.1. Alpha 1 is 0 because alpha 1 is this angle where the line A meets the point, because that is this axis, that angle is 0. Alpha 2 becomes 26.5, so this angle, which is from the top to here, right? This is how we should draw this figure. That is alpha 2, and that gives is 26.5. Now how did I get alpha 2 is 26.5? By using Pythagorean theorem. So alpha 2 is this line, right, which is the hypotenuse of this right angle triangle. So we know this is 5 and this is 10. So this is root of 5 square plus 10 square, which is 11 something. That, and then you take the inverse of that, you get the angle, right? So you get the hypotenuse, then you take the sine inverse of the hypotenuse. Sine inverse of the hypotenuse, adjacent side, opposite side divided by hypotenuse. If you take the sine inverse, you get the angle. So that's how I found the angle to be 26.5. I'll leave it to you to figure it out, but that is an angle from this point to this point. Again, you can figure that angle out, alpha 2. Once you plug all that in, you get this value for E, field intensity. Okay? All right. I hope that was clear enough. Let's look at problem 415 on slide 18. Here, the electric charge is distributed along an arc located in the xy plane. So it's still a line charge, that's why you see rho L. And it's defined by r equals 2 centimeters and phi is between 0 and 45 degrees. So it's a part of an arc. It's not a full circle, but a part of a circle called an arc that only goes 45 degrees. So that is given, and rho L is given, microcoulombs, remember that. So find E at a certain point on the z-axis and then evaluate it at the origin, z equals 5 centimeters, z equals minus 5 centimeters. So this is the formula to use, line distribution, and then dq equals rho L dl. So this portion becomes dq, I think is what I'm trying to also show. This comes from our own textbook, so you can take a look. Anyway, let me open up 415 on my notes. So here it is. So we have this little arc. It only goes from x equals 0 to x equals 45 degrees, and so we have to apply this formula. E equals 1 by 4 pi epsilon. Our unit vector of this r dash, r prime. This r prime business is in our textbook. It's a little confusing, but hey, it is what it is. So you put this magnitude of r prime in the denominator, square of it, and then on the top you have rho L dl prime. Okay, so dl is for cylindrical coordinates, it's like this, right? So we are only interested in E on the z-axis, so dl just becomes like this, or dl, the scalar, becomes r d phi. Okay, so we're only interested in this plane, right? Okay, now r prime, which is a unit vector in this direction, right? This is r prime, is like this. Now how do I get this? This, let's see. So this vector O to z, right, is this plus this, right? O to a and a to z. So using that, a to z is this r prime. You can then write OA equals OZ minus AZ, which is really what we are doing here, right? OA is this, no, OZ is this unit vector z with a height of z, and this is given to be 0.02, right? What is the value given here? 2 centimeters, right? So that's why it's 0.02 meters. So you can write this vector as this, okay? So that vector is known. Now how do you find the magnitude, how do you, I'm converting it into XYZ. And the reason I did that is, I'll be honest and tell you, this problem, the part A is, the textbook has the answer at the back. So I looked at the answer and it is shown in Cartesian coordinates. I thought, we are working in cylindrical coordinates. Why can't we just stick with cylindrical? But because the answer there was in Cartesian, I thought, okay, let me convert everything to Cartesian, because all the others also we can write in Cartesian. So anyway, look up the method. I hope you haven't forgotten, when you have a vector like this, how to convert it into a vector in XYZ. Okay, so that's what I did. Then the unit vector becomes the top vector divided by the magnitude, right? So how to find the magnitude of this, I'm sure you know by now. Please take a look. So the unit vector comes out to be the original vector divided by the magnitude. Okay, all right. Then E now can be found using this formula, right? You need the unit vector, then you multiply by all of this and you integrate, right? So integral phi equals 0 to pi by 4, there's only one variable, which is phi in this case, this unit vector times the rest of it. So if you do that, you will get, after some jugglery and some complicated formulaing, it comes out to be this value, 900 by 0.02 square with a 3 by 2, and then this XYZ coordinates. And this is volts per meter because this is an electric field. Now at a certain point, let's say the origin where everything is 0, this is the value of the field. At z equals 5 centimeters, this is the value of the field. At z equals minus 5 centimeters, pretty much the same thing. Only thing that changes is the z coefficient goes from plus to a minus. Okay, so this is how you solve where you are asked to find the field intensity when you just have this little arc of wire, not the whole circle, right? We have seen how to solve for the whole circle, but you only have 45 degrees of that whole circle, and that's carrying a charge. Then what would be the value here? I'm sure there's other methods of doing this, but this is the method I thought was easy enough to do. So here it is. Take a look, and if you have any questions, let me know. Okay. So that was example 415. Okay, slide 19. Oh, sorry, I called it example 415. It's problem 415 on slide 18. Okay, moving ahead, Gauss's law. You know, when you have all these laws, you're going to have some problems, right? Examples. So here I walked you through how to find the formula, this formula, if you're given a point charge and we need to find E at a certain radius r, right? At a certain distance r. So you have to create this Gaussian surface and you do a volume integral. Okay, so I won't go too much into it. I hope this was clear. Of course, I do want you to look at example 3.5 because there we did a sphere, and a lot of the theory here on how to do this triple integral comes from example 3.5. It's all in your textbook, so please go and take a look and that will help you. This is easy enough for a line charge. There's a double integral here, surface integral, and because this is a cylinder, not a spherical thing, and here you can see how to solve this. For an infinite sheet of charge, here's the value of the field intensity. For a uniformly charged sphere, this is an interesting example. The sphere is fully charged all over the sphere. Now you have two situations. You want to know the D or E inside the sphere, and then you want to know the charge or the field outside the sphere, right? So in this case, r is greater than the radius of the sphere. In this case, r is less than the radius of the sphere, the radius being a. So there are two answers. In the first case, 0 is less than r is equal to less than a, that is inside, this is the value, and if it is outside, this is the value. Okay? All right. Problem 427. So I copied this from somewhere else just to create a graphic that we can look at. But let's read the problem 427. So there's an infinitely long cylindrical shell. So this actually, we only take a little piece, h, but in theory this thing goes on and on. So it's an infinitely long cylindrical shell extending between r equals 1 meters and r equals 3 meters, right? So inside this, there is a sphere, there is a cylindrical shell. And I think I have another drawing, so don't get hung up on this drawing. But this I just brought to show you how to apply the limits and the formula, okay? But this is not the shape of what we are looking for. We are looking, which in fact, let me show you 427. So this is what the shape is, right? It is a cylindrical shell with a hollow in the inside and then nothing outside. But the shell itself, I hope you can tell from my drawing, has an inside radius of I think 1 meter and an outside radius of 3 meters. Okay, so that is the real shape, but you need to create a Gaussian surface, right, to solve the problem. The Gaussian surface gives you the total charge inside, right? So apply Gauss's law to find D in all regions. That means you have to find D inside, in the hollow area, then inside the shell itself, and then outside, right? 3 different regions. It has a uniform charge density. We don't know what exactly it is, but they just call it rho V0. Now, ds, I think, is why I brought this drawing. Ds is to be shown like this, right? Because it's normal to the surface and to the Gaussian surface, remember. And then the surface integral on this surface is written like this, integral d dot ds, where both are vectors, which become scalars because we do the dot product. So the r disappears in this case because it's in this direction, and then you're left with dr d phi dz, which for a spherical surface or cylindrical surface is actually this. When you apply these limits, z equals 0 to h, the height, and phi equals 0 to 2 pi, which is the entire 360 degrees. Okay, so this is part of the lesson, but the more important lesson is to solve this problem. Okay, so charge density is some value for r lying between 1 and 3. So if r is here in the middle of the shell between 1 and 3, you apply Gauss's law, you think of a surface here, and that surface and that Gauss's law will be like this, right? Because I told you already, let's look at Gauss's law here. It's d dot ds, so that's r dr multiplied by whatever is the ds value here, or the ds coordinates here. So that gives you the total charge contained in this cylinder. Now we are only taking a certain section of length L. We obviously can't deal with the whole infinite thing all at once, but if we can write a formula for L, that helps. And how does that help? Let's do the problem so you can see. So for QL, which is just for a length L of this shape or this cylindrical shell, Gauss's law will be this. Now QL is charge density into volume. So charge density times volume of this surface is, and remember, R is a variable anywhere from this point to this point. The maximum it can go is obviously 3, but the minimum is 1, and so 1 to some value r. So that density or charge QL can be written like this. Okay. Now to integrate this, to integrate the left side, we do all this stuff. So RdR, and then ds becomes r d phi dz for a spherical surface like I show here, right? This ds becomes this. We have seen this in the past. So now you can integrate this whole thing as a scalar. Luckily, all the vector stuff goes away. The constants such as dr, I'm going to bring dr out and integrate over whatever is left. So we have r d phi dz. So if you integrate this, you get dr times 2 pi rl, which I think I also show here. Yeah, 2 pi dr times 2 pi rh. So this integral, now you equate, right? According to Gauss's law, whatever is on the left side equals the total charge in the shape. So the total charge we just found to be this. The integral comes out to be this. So if you equate the two, the left hand side equals the right hand side, and from there you can find dr. Once you have dr, you can write the vector dr by writing this unit vector r with a hat and the rest of whatever was dr. And r runs from 1 to 3. For r greater than 3, right? For r greater than 3, we can definitely say what is the charge inside by using a variation on that formula, right? I talked about this formula. So now instead of r, we just put 3, right? Because now we are looking at it from the outside. So the volume of this surface is pi L this, and then you multiply that with the charge density, the volume charge density, you get the total charge, which is this value. Okay? So all this does is give you the volume, right? Remember that. Then you multiply by the volume density. So in this case, you integrate the left side and you set it equal to the right side, same as before. So dr now, the numerator is different, right? It's this. The left side is still the same because nothing changes as far as the Gaussian integral is concerned. So dr now is 4 PV0 by r, because a lot of these things fall off. See, that L that we assumed went away, right? So dr is in terms of known values such as r and rho v0, and so you can write dr as this when r is greater than 3. Now when r is less than 1 meter, that means in this hollow area, if you apply the same formulas, you can, and common sense will tell you that the field intensity there is 0, or the flux density there is 0. Okay? Alright? So that's how you solve this problem. I hope this was okay for you to understand. What else can I tell you? Yeah, remember how we did this integral, right? Or the left side integral. This, the Gaussian surface, if you assume it's outside, it really doesn't depend on, this hollowness, or these r equals 1 meter, r equals 3 meter, doesn't matter, because it's doing the integral on the whole. If you created a surface all around this, that is the surface. Hence, it is the same in either case. Okay? I hope that was easy enough to understand. All right, I'm going to move on to the last section, electric potential. So remember these formulas on how to calculate the potential difference between 2 points in terms of the field intensity, right? This is slightly different from our circuits business, right, where we used KCL, KVL and all that stuff. Here we are struggling with electromagnetics, and here we have a lot of integration to do to come up with the voltages. But remember these formulas. This is what we are going to use. Okay, so here is an example of where we have point charges. So we have some simple small charges, minus 4 microcoulombs and 5 microcoulombs, located at these 2 points. Find the potential at a third point, assuming 0 potential at infinity. So our reference point is always infinity. There it's 0. Once we have that, then we can use this formula, right? And so you'll see how, when there's only 2 Q's, Q1 and Q2, how to apply the formula and how to find the magnitudes that are required for the denominator, which is the difference of the 2 vectors. Okay, and r is the vector from the origin to the point of interest 1, 0, 1, and r1 and r2 are the vectors from the origin to where the charges minus 4 and 5 are actually located, right? So once you know those 2 vectors, then you can do the difference and find the magnitude in this way. So this is a short form way of writing it, but I'm sure you know what this means. Then to find the voltage or the potential at that point 101, you use this formula, okay, and it comes out to be a pretty large kilovolts. Again, I'm asking you the question, why is there such a large potential when you have such small charges? Something to think about. All right, I have a few more problems, so let's hurry on. Example 4.7 is in your textbook. It's actually you're deriving a formula and showing you some electric lines of force, field pattern. I am not going to spend too much time on this, but please read this yourself. A dipole, as we have seen in the past, is where two charges of equal magnitude are created in one object, and one is a positive charge and equal negative charge. If they are located like this, with the center being the origin, and if you want to find the field intensity or the potential at a third point, then how do you go about it? Here are some angles, and then it comes out to be like this, where P is the vector from the origin, which is the center of the dipole, to the point of interest. R is a unit vector in the direction of R, and then you have the rest. So this gives you the potential, and once you have the potential, you can find the E, right, the electric field intensity using this formula. Electric field intensity from potential, you just have to do the gradient, that means multiply by the del, or do the del on it, and then put a negative sign, okay, that gives you E. So he shows you how to do it. Please take a minute and go through it. All right, I got, I think, 2 or 3 problems. Okay, given the potential, this is from somewhere else, but I thought this was a good problem to solve. Certain potential is given. It's in spherical coordinates, right? R, theta, and phi. But this is a scalar quantity. Even though it's written like this, there's no coordinates really. It's just given using these factors. So the scalar value of some electrical from some vector, okay. So find the electric field intensity, find the electric flux density, calculate the work done in moving a 10 microcoulomb charge from a point A to point B in this field, okay. So these 3 things are being asked. So here are some formulas. First of all, to find E given this potential, you can use this formula. D is a simple epsilon times E. Then the work done is W, right? And W is also related to the potential and this field intensity using this formula. So you can see how I use these formulas in this example. We may not have too much time to go through it. So there's V, there's E being calculated as a vector, and then D is just this. D at a certain point, you punch in those numbers and you get a D as some picocoulombs with a unit vector attached to it. Work is from the previous formulas I showed you. You can do Q times an integral, and that integral is also the potential, because we know VB and VA can be easily found from given V, right? Just put in the coordinates and you can get VB and VA, and the work is then so much, okay? All right. So that's all I'm going to look at for that problem, and then we have the very last 2 problems, and then no more. Now these 2 problems are connected, even though they are from the back of the chapter, 433, 439. 433 is like a derivation. So there is a show that the electric potential difference V12 between 2 points in air at distances r1 and r2 from an infinite line of charge with density rho L along the z-axis is given by this. So once you have this, we have some specific values given. It's an infinite line of charge, no doubt, but the actual rho L and R1, R2 are given. So how do you put some numbers to this formula. So that's what it is. And 433, it's an infinite line of charge, something like this. And so I show you how to start with the given E along the z-axis. Then using V1, 2 is the integral of that E, and dl is rdr. You integrate, you get V1, 2 to be this. It has a natural logarithm r2 by r1. So here you have to find that r1 and r2 and the magnitudes actually. So this drawing will help you to figure out what the two vectors are for the point of interest. So we are moving from 0 to A, but the line of charge is actually not on the z-axis, it's parallel to the y-axis. So see how that formula can be used. But you must be careful in finding R1 and R2, the magnitudes in particular. Okay? And then you substitute all that, and you should be able to get this value of minus 117 volts for VAB, which is the potential, or the potential difference is what he's asking for. Okay, apologize again, we went over, but that is the end of part A, both the theory and the problems. Please spend enough time on it so that you're comfortable with all the concepts and how to use the various integrations. Because this whole chapter depends on doing these volume and surface integrals well, and also understanding these laws, the Gauss's law and the earlier laws, some of them, the divergence theorem and the Stokes theorem, plus Gauss's law, of course. Okay, and then understanding line charge density, volume charge density, surface charge density, etc. All right. Okay, I'm going to stop.